introduction, and also thanks a lot for the invitation to speak. I'm really pleased to be able to speak to everyone here today. Thanks a lot for coming along. I hope you enjoy the talk. So, as you maybe got from the introduction, I'm someone who really likes studying prime numbers, and today I'd like to talk about a question on prime numbers that's a very old but pretty simple to state question, which is just asking how many prime numbers are there in an arithmetic progression. The main question that I'd like us all to think about today is, well, you can think of it as a challenge that you choose your favorite three numbers, x, a, and q, and I have to try and work out how many prime numbers there are which are less than x and leave a remainder a after dividing by q, so in the residue class a modulo q. And I'll write pi of xqa for this count of the number of primes in a given residue class. So this is a exceptionally important quantity to understand from the point of view of prime number theory, and it's a very famous theorem of Dirichlet that provided your residue class A and your modulus Q are coprime to one another, then there are infinitely many prime numbers which are in the residue class A modulo Q. So in terms of our original question, if x is large enough, then pi of xqa gradually grows and grows and grows, because there's infinitely many numbers in the residue class A modulo Q. But Dirichlet's theorem on its own doesn't tell you how many primes there are or what the distribution of primes is. And certainly if there's a few trivial cases, if q is bigger than x, then there's at most one whole number which is less than x, is non-negative and is congruent to a modulo q, and so there's certainly at most one prime. And similarly, if a and q have a common factor, anything that's in the residue class a modulo q must be a multiple of that common factor, and so there can be at most one prime. So those are somehow the trivial cases of my basic question, but I'm maybe interested in trying to refine Dirichlet's theorem in some way to understand how densely the primes occur in this residue class a modulo q. So just to give a very explicit example, it might be that you chose x as being 1 million, q as being 1000, and a as being 33, and you can then do a calculation on a computer, and the number of primes which are less than 1 million and are in the residue class 33 mod 1000, so that means the final three digits of the prime number are 033. It turns out there's 172 of them. And in fact, regardless of what you chose a to be, provided it doesn't have a common factor with q, in this case, the number of primes which are less than x and congruent to a modulo q always lies between 172 and 218. And so you might guess from this numerical example that at least in the situation when q is a reasonable amount smaller than x, actually the primes are fairly evenly distributed in these different residue classes. For this particular numerical example, regardless of what choice of a you had, there wasn't too much variation in the number of primes in that residue class modulo q. And this is actually a typical feature. You could do much more extensive numerical investigations. And so this example is actually quite exemplary of the sorts of questions I'd like to think about, where x is certainly noticeably larger than q, but maybe not arbitrarily large compared to q. And I'm thinking about how evenly distributed the primes are in the given residue classes. So Dirichlet's theorem is one of the most famous theorems about prime numbers. It was basically the theorem that started off analytic number theory, which is the field that I work on. But unfortunately, we're not able to refine Dirichlet's theorem a huge amount. So the natural question, if you're trying to think about quantitative versions of Dirichlet's theorem, is asking maybe if x is large, how big does x need to be to get roughly the same number of primes in each arithmetic progression, and to get a good estimate for the number of primes in each arithmetic progression. And we do have a result of this type. It's a very important result known as the Siegel-Walfisz theorem. And this says that provided q is fairly small compared to a, where fairly small means bounded by log x to the power some fixed constant, so maybe log x to the power 100, then we do have a asymptotic formula for the number of primes which are in each residue class modulo q. And the Siegel-Walfisz theorem is saying, at least if you look at big enough numbers x and q that satisfy this inequality, then the primes are roughly equidistributed in the different arithmetic progressions. So this is similar to what we saw in the numerical example, where when we were taking x to be 1 million and q to be 1000, we saw that pi of xqa didn't change too much as you changed a, and the primes are actually evenly distributed amongst these residue classes, provided you remember that the residue class always has to be co-prime to the modulus. So the Siegel-Walfisz theorem has a huge number of applications, particularly in analytic number theory, but also elsewhere in number theory and beyond. But unfortunately, for lots of applications, you'd really like to take q to be bigger than log x to some fixed power. Maybe it'd be really nice to take q to be of size square root x or something. So in my numerical example, I had x to be 1 million and q to be 1000, and so q was of size roughly the square root of x. So it would be very nice for applications if you could improve on this range of q, but unfortunately, improving on this range of q is essentially a reformulation of a very famous difficult problem which is related to the Riemann hypothesis, known as the problem of Siegel zeros. So these are potential very bad exceptions to the Riemann hypothesis that we think shouldn't exist, but our tools at the moment just seem incapable of ruling them out. But if these very bad counterexamples to the Riemann hypothesis did exist, then it would be the case that the primes are not evenly distributed when q gets a bit larger than log x to some fixed power. And so you'd really need to understand this difficult question related to the Riemann hypothesis and make some big progress towards the Riemann hypothesis if you were going to improve on the Siegel-Walfisz theorem. So this is maybe a little bit depressing that we have this classical result, the Siegel-Walfisz theorem, that tells us a nice result about primes in arithmetic progressions, but it only holds in a slightly restrictive range. But to make progress on this range, we need to make progress on some very difficult problem that is closely related to the Riemann hypothesis. So I'd like to talk a little bit about the Riemann hypothesis and its relevance to this question. So the Riemann hypothesis is about a complex analytic function which is called zeta of s, and it's really about the zeros of this function zeta of s in the complex plane. So I've drawn a picture of the complex plane here, and when the real part of s is bigger than 1, essentially the zeta function is fairly well understood, and it turns out that the zeta function has no zeros in this region. Then there's one magical property of the zeta function, that it satisfies the symmetry about the line the real part of s equals 1/2, which means that since we understand the zeta function whenever the real part of s is bigger than 1, we also understand it whenever the real part of s is smaller than 0, and there's essentially no zeros of the zeta function in this range, apart from some trivial zeros that we don't need to worry about for the purposes of this talk. I guess one small point is I can't see the chat, so if anyone has any questions, please feel free to interrupt me at any point as I'm speaking.
That's fine. And just to say, YouTube's working again now, so we're all good. I'll monitor the chat for you.
Okay, great. So where we were was that there's this function, the zeta function, that's very important from a number theoretic point of view. We essentially understand it in this region that I've shaded in blue, when the real part of s is bigger than 1, or when the real part of s is smaller than 0. But the zeta function remains very poorly understood in this so-called critical strip when the real part of s is between 0 and 1. And the Riemann hypothesis is about where the zeros of this function are. And if you do numerical experiments, you find that all the zeros that we know about, and we know about maybe the first 10 to the 10 zeros of the Riemann zeta function or something, all have real part equal to 1/2. And so the Riemann hypothesis is the claim that this isn't just true for the first 100 billion zeros, this is in fact true for all zeros. But we have no idea really how to prove this. We know that all of these zeros have to have real part between 0 and 1, and the claim is that they should all have real part equal to 1/2. So this is sometimes dubbed the most famous or most important problem in mathematics. The Clay Mathematical Institute gives you a $1 million reward if you solve the Riemann hypothesis. And the specific zeros of the Riemann zeta function are exceptionally important because they determine lots of things about the distribution of prime numbers. So the Riemann hypothesis on its own doesn't tell you too much about primes and arithmetic progressions, but the Riemann hypothesis is just the tip of an iceberg of a whole set of conjectures for related so-called L functions, where we also believe a Riemann hypothesis should hold, and all the zeros should lie on some nice vertical line. And so we believe that there should be a generalized version of the Riemann hypothesis, which holds for all these more exotic versions of the Riemann zeta function. And one form of these exotic generalizations are the Dirichlet L functions. So the generalized Riemann hypothesis, or at least one formulation of it, is if you look at all these Dirichlet L functions, then all the non-trivial zeros of these Dirichlet L functions also all line up on this vertical line with the real part equal to 1/2. So this is a big generalization of the Riemann hypothesis, and the generalized Riemann hypothesis in this form tells you a huge amount about primes and arithmetic progressions. So I mentioned before that the barrier to extending the range of Q, the size of the modulus, is this problem of so-called Siegel zeros, which would be very bad counterexamples to the Riemann hypothesis, where this would be a putative zero that doesn't have real part equal to 1/2, and in fact has real part very close to 1. So it's almost as big as it possibly could be. But if you assume the Riemann hypothesis, or the generalized Riemann hypothesis, then these Siegel zeros certainly can't exist. And one consequence of the Riemann hypothesis is that you get a very good and accurate formula for the number of primes in any given arithmetic progression. So this allows this formula, this alternative form of the generalized Riemann hypothesis, which is equivalent to the standard form of the Riemann hypothesis. So if you can prove this formula for primes and arithmetic progressions, not only would you have got a very strong answer to my original question, you'd have also earned yourself $1 million, and you'd have proven the standard form of the generalized Riemann hypothesis, that all the zeros lie on these special lines if you have one of these accurate formulas for the number of primes in an arithmetic progression. And so one consequence of this is that if you assume the generalized Riemann hypothesis, then you get this equidistribution of primes in different residue classes modulo q, for q in a much bigger range, for q going all the way up to essentially the square root of x. So if you remember before, unconditionally, we had that the primes were equidistributed in arithmetic progressions, but only in a very restrictive range of q being less than or equal to log x to the power 100 or log x to the power 1000. But here, if you assume the generalized Riemann hypothesis, you're allowing q to be much bigger, and q can be almost as large as the square root of x. So in my original numerical example, in that example, I had q being of size exactly the square root of x, and so that's right on the cusp of when this generalized Riemann hypothesis bound would allow us to conclude that you get roughly the same number of primes in every possible arithmetic progression. And it turns out that these two questions are exceptionally closely related, that the zeros of Dirichlet-Held functions really completely determine the distribution of primes in arithmetic progressions. So if you had a weaker form of the generalized Riemann hypothesis, where all the zeros of Dirichlet-Held functions had real part at most 3/4, then, sorry, there's a typo here. Instead of q going up to theta, it should be 1 minus theta. So if q is less than x to the power 1/4, in the case that if you have all real parts at most 3/4, then you get this equidistribution of primes in arithmetic progressions. So the 1/2 for this real part of zeros corresponds almost precisely to this improved range, the 1/2 in the exponent q going up to x to the power 1/2. And correspondingly, if you had a quasi-Riemann hypothesis where all the zeros of Dirichlet-Held functions had real part at most 0.75 or theta, then you'd have a correspondingly slightly weaker result where q goes up to x to the power 1/4 or 1 minus theta. So there's this perfect balance in terms of how strong a result you can get towards the Riemann hypothesis, and how well you can get equidistribution of primes in arithmetic progressions to these slightly larger moduli q. So in summary, if we assume the Riemann hypothesis, then sometimes we can get these very strong bounds. So unconditionally, we can handle the range for q going up to log x to some power. And if you assume the Riemann hypothesis, you can allow q to be much larger, and you can allow q to go up to roughly the square root of x. But for this question and this formulation about how big q can be compared to x when you still get equidistribution of primes, we believe that actually you should be able to prove a result that goes far beyond this generalized Riemann hypothesis bound. So it's a conjecture of Montgomery, which we believe to be much harder than the generalized Riemann hypothesis, that in fact you get equidistribution amongst all the different residue classes A modulo q, whenever q is just a tiny bit smaller than x. So rather than q having to be smaller than x to the power 0.5, instead we can have q being at most x to the power 0.99999, and you'd still get this equidistribution. So although there's not a natural corresponding statement, if you look at the question in terms of zeros, when you look at this question in terms of primes, we believe actually there should be this far-reaching extension that would go far beyond just the Riemann hypothesis. Morally, this would be saying something about the actual values of these low-lying zeros across lots of different L functions, and that they would somehow look as if they're randomly distributed when you look at a collection of lots of different L functions. So it would be asking a much more subtle question about the distribution of zeros. And fundamentally, this slide summarizes everything that we know about my original question. Unconditionally, we're restricted to q being very small, of logarithmic size. And to make any progress, we'd have to make progress on this famous problem about z equals zeros. But if you assume a well-known conjecture, such as the Riemann hypothesis, then you can extend the range of q a lot, and you can allow q to be of size almost the square root of x. But we believe the actual truth for this equidistribution problem should be much, much further on. And Montgomery's conjecture says you should be able to take q almost as large as x. And so this is what we know assuming famous plausible conjectures, and then what we actually believe to be the truth, even though we have no idea of how to prove Montgomery's conjecture, even under assumption of fairly well-known or standard conjectures like the Riemann hypothesis. So Montgomery's conjecture goes a long way beyond the Riemann hypothesis. So that's not the end of my talk, because it turns out that for many applications, it's very important to go beyond this Siegel-Waalfitz range, but it's not important that we know this for each q individually. It's sufficient to know it for most q. So the Riemann hypothesis tells you you have equidistribution of primes for every individual value of q, which is smaller than the square root of x. But the Bombieri-Vinogradov theorem is an unconditional result that says, so on the zero side, it says that for most Dirichlet L functions, there are no zeros with real part much bigger than 1/2. So the vast majority of zeros do lie exceptionally close to this critical range in a certain quantitative sense. And so this is often dubbed the Riemann hypothesis is true on average. And in the setting of primes, there's a natural analogous statement, and this says for most values of q less than equal to the square root of x, we do have this equidistribution in every residue class A modulo q, but there's potentially a few bad values of q where you wouldn't have this equidistribution. But saying that this is true, so this is sort of saying that the Riemann hypothesis is true on average, and you correspondingly get strong results about primes and arithmetic progressions if you're allowed to look at just average values of q rather than the worst case possible values of q. So if you allow a few small number of exceptions. And the key point of this result is that there's lots of auxiliary arguments where this unconditional result is just as good as the Riemann hypothesis itself. So for example, there's a whole area of number theory, which is known as sieve methods, which is a way of trying to study the primes. And sieve methods often require you to have knowledge about primes and arithmetic progressions, but they only ever require this knowledge on average, at least in typical circumstances. And so from the point of view of sieve methods, the Bombieri-Vinogradov theorem is as good as the Riemann hypothesis. And so there were several results that initially the result was proven conditionally, assuming the Riemann hypothesis. And then later on, people were able to make the result unconditional because the Bombieri-Vinogradov theorem is an adequate substitute for the Riemann hypothesis, for the generalized Riemann hypothesis. So the Bombieri-Vinogradov theorem is this very powerful unconditional substitute for the Riemann hypothesis, and in some sense is the strongest partial result we know towards the Riemann hypothesis, or the generalized Riemann hypothesis. So this is quite satisfying that even though we very quickly run into very difficult problems that are connected to the Riemann hypothesis, if we try and prove things unconditionally for each individual q, we can actually get unconditional results that are almost as good as the Riemann hypothesis for applications if we're just allowing ourselves to look for most q. But just as we believed that you should be able to go beyond the Riemann hypothesis for each individual Q. We also believe that we should be able to go beyond this threshold of the square root of x when we're looking at Qs on average. And so this has actually been a very famous problem in analytic number theory, which is sometimes called breaking the square root barrier or something like that, which is trying, as a proof of principle, to go beyond the Riemann hypothesis and allow yourself to show that at least for most Q, you get this equidistribution. And the key point of this is that you might be able to unconditionally prove a result of this type, because we already know the Bombay-Vinogradov theorem. And so this might be an unconditional result that goes beyond the Riemann hypothesis, at least in this average sense, by allowing yourself a few bad exceptional values of Q. So this would be saying that at least for most Q, you get equidistribution of primes in arithmetic progressions modulo Q, with Q being allowed to be a little bit bigger than the square root of x. And psychologically, I find this a very appealing problem, precisely because square root of x is exactly this Riemann hypothesis barrier, and it's morally saying something which is going slightly beyond the Riemann hypothesis in some sense. But it turns out that there's a big threshold of difficulty. It's not that you can just tweak the proof of the Bombay-Vinogradov theorem, precisely because the Bombay-Vinogradov theorem is morally saying something along the lines of most zeros lie either on the half line or very close to the half line, whereas this would have to be talking about something, some sort of distribution of the zeros across many different L functions, which is a qualitatively completely different order of difficulty. But as well as it being maybe naturally appealing, a question for me and other analytic number theorists as a challenge to go beyond this Riemann hypothesis range, it turns out that there's several questions about prime numbers where this threshold of the square root of x is an absolutely critical threshold as to whether you get a result or not. So we heard in the introduction that Zhang's work on bounded gap string primes had this feature, that the key technical idea that he really proved was a result about primes in arithmetic progressions, where he was able to go slightly beyond this square root of x range. Similarly, the Titchmarsh divisor problem is a famous problem due to Titchmarsh about the distribution of prime numbers. And it turns out here that it's questions about primes in arithmetic progressions where the modulus of the arithmetic progression is of size about the square root of the size of the primes that we're looking at, which is the key critical threshold for that problem. Similarly, Artin made a famous conjecture that any number is for any fixed number a, which is a non-square, a is a primitive root modulo p for infinitely many primes p. And Hooley was able to prove Artin's conjecture if he assumed a generalized version of the generalized Riemann hypothesis. But again, the key thing here and the key critical threshold is a question about primes in something like arithmetic progressions, where the modulus is around square root of the size of the primes. And another result of Hooley, Hooley proved a old question of Hardy and Littlewood, that there are infinitely many primes of the form x squared plus y squared plus 1, and got an asymptotic formula for these. And for this question, again, the key technical difficulty was understanding primes in arithmetic progressions, where the modulus of the arithmetic progression was of size roughly square root of the size of the primes. So it turns out that as well as there being this sort of psychological change in the order of difficulty, and moving beyond this Riemann hypothesis range, this threshold of the square root of x is actually critical for lots of different applications in questions to do with prime numbers. And so this is why this square root of x barrier has become a sort of popular phrase in analytic number theory. So there was some pioneering work in the 1980s by Bombieri, Fouvry, Friedlander, and Ivaniec, and they were able to break through this square root of x barrier, at least in special circumstances. So I'm going to write down a couple of slightly technical results here. Please don't be intimidated by them. It's just that I feel I need to state what their results are. And the first result was that if you were only ever considering primes and arithmetic progressions to maybe a fixed residue class, and you were looking at moduli which were only a very, very small amount bigger than x to the 1/2, so x of size x to the 1/2 plus delta, where we're really thinking of delta being very, very small indeed, then they showed that you could improve upon the trivial bound by a factor of delta squared. So if delta tends to 0 as x tends to 0, then this is getting a non-trivial result, and it's saying for most moduli q of size very close to the square root of x, you have something close to equidistribution. But the key point here is that you're going beyond the range that's required from the Riemann hypothesis. And so you're allowed to take moduli which are a very small amount bigger than the square root of x, even though you lose something on the quantitative side of all the estimates. And as I mentioned before, one of the most important applications of these equidistribution results is that the Bombieri-Vinogradov theorem is as good as the Riemann hypothesis from the point of view of sieve methods. And the second result of Bombieri, Friedlander, Ivaniec allowed you to take moduli which went significantly beyond x to the 1/2, so they could go up to x to the 4/7, and they had a sort of technical formulation about exactly what this was. But the key point of this result was that it was exactly the sort of result that you really need for sieve methods. And so from the point of view of sieve methods, it's as if you can extend the equidistribution of primes, not for just for q going up to the square root of x, but using this result, you could now go for q up to x to the 4/7. But again, there were various technical restrictions, so it wasn't a full answer to the challenge problem. But from the point of view of sieve methods, this was totally adequate for lots of different applications. Then much more recently, as I mentioned before, Yiteng Zhang proved his famous result about bounded gaps between primes. And the key input in Zhang's work was a result about primes and arithmetic progressions where the moduli go a bit beyond x to the 1/2. So he allowed you to take moduli of size x to the 1/2 plus some small constant, provided all the prime factors of the moduli that you considered were very small. So if the moduli were just products of lots of different small prime numbers, then he allowed you to go beyond this x to the 1/2 barrier. So again, this is a sort of technical variation on the Bombieri-Vinogradov theorem, and this shows that you do get equidistribution for most q going beyond x to the 1/2, provided you restrict your attention just to moduli q with lots of small prime factors. And this was refined by the joint polymath project. And one technically important thing for the question of bounded gaps between primes was that these results were very uniform with respect to the residue class. So Bombieri, Friedlander, Ivaniec, and Zhang both proved sort of technical variants that did go beyond x to the 1/2 in some way, and so did prove some technical statement that in some sense was going beyond the Riemann hypothesis on average. And correspondingly, these ideas had various applications to do with prime numbers. So one consequence of the ideas connected to the work of Fuvre, Bombieri, Friedlander, and Vaniec was on Fermat's last theorem. So this predated Andrew Wiles's ultimate proof of Fermat's last theorem, but using these ideas, Adleman, Fuvre, and Heath Brown were able to show that essentially Fermat's last theorem is true for infinitely many prime exponents. So it's sufficient, if you want to prove Fermat's last theorem in general, it's sufficient to prove Fermat's last theorem just when the exponent is prime. But before this work in the 1980s, various individual exponents had been verified, but it wasn't even known if infinitely many different prime exponents Fermat's last theorem held, and they were essentially able to prove that Fermat's last theorem is true for infinitely many different prime exponents, and this was the first sort of general case of exponents for Fermat's last theorem. I guess there's a technical slight issue that it was just the first case of Fermat's last theorem. The original way that people envisaged proving Fermat's last theorem was to split first Fermat's last theorem into the first case for prime exponents and then the second case for prime exponents. And everyone was working on the first case. And so this is sort of morally like proving Fermat's last theorem for infinitely many prime exponents. As I mentioned before, and as we heard in the introduction, one other consequence of these results about primes in arithmetic progressions that go beyond this square root of x barrier is that we got bounded gaps between primes when you combined Zhang's result about primes in arithmetic progressions with some earlier work of Goldson, Pince, and Yildirim coming from sieve methods. So again, it was the key input was sieve methods, and something beyond the Riemann hypothesis was essentially shown to be true on average for sieve methods, and this allowed Zhang to prove that there's infinitely many pairs of primes that differ by no more than 70 million. And for both of these theorems, it's absolutely critical that you're going beyond this square root of x barrier in both cases, even though the technical results have a little bit of restrictions to them. There were various other consequences as well. So automatically, from the point of view of sieve methods, these results of Bombieri, Friedlander, and Vaniec overnight improved a whole load of different estimates, because you could now replace lots of values of 1/2 in arguments by 4/7. This, I mentioned before that there were various problems such as primes being of the form sums of 2 squared plus 1, or the Titchmarsh divisor problem, and based on ideas such as these, you suddenly got good asymptotics or good error terms. So the result on primes of the form x squared plus y squared plus 1 is actually a very recent result just of this year. Similarly, by modifying these ideas, another recent result is improved ranges for so-called one-level density estimates for series of the Riemann zeta function. So these underlying ideas of being able to go beyond the square root of x barrier have lots of different applications in lots of different problems, both within analytic number theory, but also outside to questions like Fermat's last theorem. Of course, this result was made somewhat redundant when Andrew Wiles completed the full proof of Fermat's last theorem. Okay, so I'd like to mention a couple of new results. So again, this maybe is a technical, scary looking formula, but so I put up one technical statement of what it is I proved, but I put two consequences of this. So one immediate consequence of my work is that if we're looking at moduli q going up going beyond x to 1/2. So let's think of x to 1/2 plus 1 over 2000. So a tiny bit beyond this Riemann hypothesis range. Then for some fixed residue class, you do get most moduli Q having equidistribution in this sense, in where most means at least 99% of the moduli have this. Of course, we expect it to be true for 100% of moduli. We can't quite prove this, but this is getting the genuine asymptotic formula for the number of primes in a given residue class for most moduli that are going beyond this Riemann hypothesis range. And one technical consequence of this is that we can get explicit Bombieri-Vinogradov type results when you have moduli that have some factor which is of size about x to 1 over 21, and these can go quantitatively a moderate amount beyond x to 1/2. They can go up to moduli of size x to the 11 over 21. So this is some sort of explicit estimate for being able to go a moderate distance beyond this square root of x range. Similarly, I mentioned before that from the point of view of sieve methods, you often don't need quite such strong estimates. You can have some certain technical estimates, and my results now improve the Bombieri-Friedlander-Ivanich results for sieve methods from 4/7 to 3/5. So 3/5 is the current record for how big we're able to say something about primes and arithmetic progressions to these sorts of moduli. And from the point of view of applications in sieve theory, this means that there should be lots of cases where you have constants 4/7 appearing, where you should be able to improve it to either 7/12 or 3/5, depending on the application in mind. So hopefully this will give quite a lot of quantitative estimates to a whole load of different applications by understanding these underlying estimates about primes and arithmetic progressions. So again, the actual statements of these results are slightly complicated and look a bit messy, but what they're really saying is just in some specific weighted quantitative sense, the number of primes which are less than x and congruent to A modulo Q is roughly what you'd expect from equidistribution for most Q when I'm allowing Q to go beyond this square root of x range. And then finally, one other set of new results on equidistribution of primes and arithmetic progressions is that I'm able to get some completely uniform results, provided you look at moduli that have a convenient sized divisor. And so one consequence of this is that if you look at moduli going beyond x to 1/2, provided they have a divisor between x to the 2/5 and x to the 3/5, then for most of these moduli, you get the sort of asymptotic formula for every possible residue class coprime to your modulus. And so again, these are extensions of the previous far-reaching work of Bombieri, Friedlander-Ivanich, and of Zhang and of Fouvry, where we're able to get some equidistribution of primes and arithmetic progressions going beyond this Riemann hypothesis range. And my results are sort of having fewer technical assumptions on the nature of the arithmetic progressions that we're looking at than was previously known, and so we're able to handle a wider class of arithmetic progressions going beyond this Riemann hypothesis range. So again, this is sort of closer to the dream challenge of being able to handle all moduli which are a little bit bigger than x to 1/2. So I don't want to go into technical details of the proof, but I'd like to highlight some of the different ideas that appear in the proof, just to give a flavor of the way that lots of these arguments draw upon lots of different ideas coming from different areas of mathematics, that I think are a really fun combination of different things coming from different areas. So on a very high level overview, it follows lots of classical approaches to studying primes. So we typically start off with some sort of combinatorial decomposition of primes using ideas coming from sieve methods, where you're trying to understand prime numbers by understanding numbers with maybe 2 prime factors of given sizes, and depending on the sizes of the prime factors, you then use rather different arguments in different ranges. So we start off with a very sort of combinatorial outlook, but then to understand these questions about maybe products of 4 prime factors, where each prime factor is of a different size, we use Fourier analysis to turn the whole problem into a question about estimating some very complicated looking exponential sums. So this is, we've done some combinatorics, we've now done some Fourier analysis, we've reduced the whole problem about counting primes in arithmetic progressions to estimating some complicated looking exponential sums. And depending on the precise situation of what the sizes of the different prime factors we were looking at, there's sort of 2 big hammers that we can use to try and estimate exponential sums. So one big set of techniques comes from the spectral theory of automorphic forms and ideas coming from the Kuznetsov trace formula, in particular the pioneering work of Desoury and Vaniech. And the other big hammer we can apply is that you can get some very good estimates for exponential sums using ideas coming from algebraic geometry and relating these exponential sums to versions of the Riemann hypothesis, but now for curves over finite fields. And for this analog of the Riemann hypothesis for curves over finite fields, work of André Weil and then far-reaching generalizations of Deligne allow you to prove the Riemann hypothesis, and this corresponds to getting exceptionally strong bounds for certain exponential sums. And in some of these ranges, ideas coming from the spectral theory of automorphic forms are more powerful. In some of these ranges, bounds coming from algebraic geometry are more powerful. It doesn't matter at all if you've never heard of the Kuznetsov trace formula or some of the things that I'm mentioning here. I'd just like to emphasize the spirit of the argument, where we're starting off doing combinatorics, then we're doing some Fourier analysis to reduce to exponential sums, then we're using ideas coming from automorphic forms or from algebraic geometry to try and handle these exponential sums. And then there's some delicate process of trying to manipulate all the sums so I can use these techniques in the most efficient way possible, hoping that I can cover all the different terms that appear in my combinatorial decomposition at the beginning. And maybe one of the key new ideas in my work is coming up with different ways to combine these ideas coming from algebraic geometry with these ideas coming from the spectral theory of automorphic forms. So this is very much on the technical end of analytic number theory. So I think I will not go into a huge amount of detail here, but all I'll say is that the reason that automorphic forms appear is that it's very natural in these sorts of questions that you arrive at certain sums of special exponential sums called Klustermann sums, and the Kuznetsov trace formula is just this amazing method for allowing you to turn certain sums of Klustermann sums into certain averages of Fourier coefficients of automorphic forms. And so if you can understand Fourier coefficients of automorphic forms, you can get good bounds for sums of Klustermann sums and correspondingly estimate the quantities that come out from doing Fourier analysis that I mentioned on the previous slide. On the other hand, the other key input was estimates coming from algebraic geometry, And this was one of the key innovations in Zhang's work on primes in arithmetic progressions. And the key point here is if you have some exponential sums that are somewhat algebraic in nature, then you can relate these algebraic exponential sums to the size of certain cohomology groups for some associated curves and varieties over finite fields. And then if you understand questions like the Riemann hypothesis for the associated curves and varieties, then you can get good estimates on the cohomology groups, which allow you to get good bounds for these exponential sums. And then you can feed that into the Fourier analytic argument to handle different ranges. Again, these estimates have certain advantages and certain technical disadvantages. So in the interest of time, I don't want to go into too many details about the new ideas, other than there was this annoying feature beforehand that the most difficult ranges, if you were trying to use the Kuznetsov trace formula, basically coincided with the most difficult ranges to handle if you're using the estimates from algebraic geometry. But I was able to refine the spectral estimates in this worst case scenario, which meant that suddenly the two approaches combined much more efficiently than they would have done beforehand, because what was the worst case scenario for both I could handle, and then the worst case scenario that was left over from the point of view of the spectral estimates was actually one of the best cases from the point of view of these algebraic geometry estimates. The spectral refinement is inspired by the amplification method, whereas maybe inspirations from the sort of transference principles from additive combinatorics were the behind the key refinements of the algebraic geometry approach. But I don't want to go into too much detail about those. And I think I'll skip this slightly more technical slide. And I will finish up just with this sort of schematic diagram of this sort of overall approach to thinking about primes and arithmetic progressions, where we have two big powerful black boxes coming from the spectral theory of automorphic forms and algebraic geometry. And then there's various different ways you can use these sorts of ideas to estimate certain technical exponential sums. And it turns out that these different techniques are more or less effective for explicit different terms that come up. And you can combine all these different terms using some sort of combinatorial decomposition. And if you understand all of these products of 3 primes, 5 primes, 7 primes, products of two numbers with one factor close to 1/2, and products of two numbers with one factor far away from 1/2, then it turns out you can use a combinatorial decomposition to turn this understanding into understanding about primes. And that allows you to understand these new results about primes and arithmetic progressions that in some sense are going beyond the Riemann hypothesis unconditionally, but in an average sense. So that's all I have to say here. Thanks a lot for listening. I hope you enjoyed the talk.